What happens when a planetary storm survives for centuries, only to begin shrinking before our eyes? We tend to see Jupiter's Great Red Spot as a permanent feature, a fixed scar on the giant planet. But new data suggests it isn't just a surface disturbance at all. It's a deep thermal engine, behaving unlike anything in Earth's atmosphere. The stability we've witnessed for generations is really a fragile balance of forces that scientists are only beginning to untangle. If these quiet cosmic mysteries are the kind that help you drift a little easier, a gentle like and subscribe lets this space continue to grow. You're listening to Sleep Astronomy, and tonight we'll explore the physics that keep this colossal storm alive and what might finally be causing it to change. Jupiter remains one of the most enigmatic locations within our solar system, despite centuries of observation. Recent technological advances in space exploration have begun to unlock the secrets held by this colossal gas giant, a world defined by endless storms and cyclones. The scientific community is currently analyzing significant discoveries made by the James Webb Space Telescope and the NASA Juno mission. These findings reveal a planet where storms have persisted for more than 3 centuries, where winds penetrate the atmosphere in intricate ways, and where the largest vortex in the solar system exhibits behavior that challenges established theories. These insights offer a new perspective on the complex and dynamic atmosphere of Jupiter, rewriting our understanding of its history and physical mechanics. The James Webb Space Telescope recently identified unexpected and intriguing structures positioned directly above the Great Red Spot. This storm has been a dominant feature of the planet for more than 300 years, yet the area immediately above it was previously thought to be relatively calm. Observations utilizing the near-infrared spectrograph instrument on the Webb telescope have shifted this perspective, revealing that the upper atmosphere is just as complex and dynamic as the visible cloud layers below. While the atmosphere above the Great Red Spot might appear unremarkable in standard optical views, the sensitive infrared capabilities of the telescope allow scientists to see thermal patterns invisible to the human eye. Researchers have detected complex arrangements, including dark arcs and bright spots that contradict previous assumptions about atmospheric stability in this region. These features are likely the result of powerful atmospheric gravity waves. It is important to distinguish these from gravitational waves, which are ripples in space-time. Atmospheric gravity waves are a physical phenomenon occurring when waves generated in the turbulent lower atmosphere of Jupiter propagate upward. As they rise, they alter the structure and radiation of the upper atmospheric layers. On Earth, a simplified comparison would be waves on a beach, creating ripples in the sand. But on Jupiter, the scale and intensity are vastly superior. The tremendous energy and turbulence generated by the churning of the Great Red Spot act as a mechanism to launch these waves. They travel vertically, affecting the dynamics of the atmosphere at much higher altitudes. Observations from the James Webb Space Telescope indicate that these atmospheric structures over the Great Red Spot exist at varying altitudes. Some regions emit higher levels of infrared light due to the presence of hydrogen in the ionosphere of Jupiter. This differentiation in height and emission intensity is a direct result of the influence of gravitational waves moving through the gas. The region located above the Great Red Spot represents a critical interface where the lower atmosphere of Jupiter meets its immense magnetic field. This is similar to how the atmosphere of Earth interacts with the solar wind, which results in auroras. However, on Jupiter, this interaction is further complicated by the presence of volcanic material from Io. Io is the most volcanically active body in our solar system, and it ejects tons of material into space. These materials combine with charged particles from the Sun to fuel the Jovian auroras and contribute significantly to the complex atmospheric dynamics observed by astronomers. Further study of these gravitational waves is expected to provide a deeper understanding of how energy is distributed across the entire planet and will enhance our general models of atmospheric processes on gas giants. Future missions are set to build upon these foundational findings. The Jupiter Icy Moons Explorer, or JUICE, led by the European Space Agency, launched in the year 2023. It is scheduled to reach Jupiter by the year 2031. Upon arrival, it will conduct detailed observations of the planet and its large ocean-bearing moons, providing more data on the interactions between the planet and its satellites. In parallel with these telescopic observations, the NASA Juno mission has made a groundbreaking discovery regarding the internal structure of the winds on Jupiter. The data indicates that atmospheric winds penetrate the planet in cylindrical layers that are aligned with the axis of rotation. This discovery fundamentally changes the scientific understanding of the atmosphere and internal structure of the gas giant. It disproves long-held assumptions that winds might be shallow or confined to surface shells, and provides new insights into the fluid dynamics of planetary atmospheres. Scientists achieve this by analyzing data from the radio signals of the spacecraft. By measuring minute changes in the speed of Juno as it orbits Jupiter, researchers can detect fluctuations in the gravitational field of the planet. These fluctuations allow researchers to peer beneath the turbulent cloud cover without needing to physically enter the atmosphere. Using high-precision measurements, scientists applied a mathematical method commonly used for studying rocky planets to model the gravitational fluctuations of Jupiter. This innovative approach increased the resolution of the data by a factor of 4 over previous models and provided a detailed view of the deep atmospheric winds. The study demonstrates that the powerful east-west zonal winds of Jupiter, which are observed as the colorful belts and zones on the surface, do not propagate radially in all directions toward the center of the planet. Instead, they penetrate inward in cylindrical layers that remain parallel to the spin axis of Jupiter. The cylindrical nature of these winds was confirmed by comparing 40 gravity coefficients measured by Juno with theoretical models. This discovery marks a significant advance in the understanding of atmospheric dynamics for Jupiter and similar gas giant planets throughout the galaxy. The cylindrical structure suggests a complex interaction between the deep atmosphere and internal planetary processes. Unlike zonal flows on Earth, which are heavily influenced by the solid surface and topography, the winds on Jupiter extend deep into the interior, unaffected by solid boundaries. These winds reach a depth of about 1,860 miles beneath the cloud tops. This is much deeper than previously thought. This depth has profound implications for understanding the internal structure of the gas giant and how energy is distributed from the core to the surface. Returning to the observations from the James Webb Space Telescope, the flow of new data continues to refine our knowledge. The telescope has revealed unprecedented details about the atmosphere of Jupiter, specifically regarding wind speeds. Researchers have detected a high-speed jet stream passing directly over the equator of Jupiter, located above the main cloud decks. This jet stream is more than 3,000 miles wide. Its discovery updates the understanding of the complex dynamics of the atmospheric layers of the planet. Using the near-infrared camera, scientists detected this jet at an altitude of 12 to 21 miles above the cloud tops of Jupiter. The jet travels at a speed of 320 miles per hour. For context, this is twice the sustained wind speed of a Category 5 hurricane on Earth. The discovery sheds light on how the different atmospheric layers of Jupiter interact, revealing the complexity of the weather systems of the gas giant. Like Earth, Jupiter has a multi-layered atmosphere. However, the dynamics on the gas giant are far more intense. The newly discovered jet stream is located in the lower stratosphere of Jupiter, just above the tropospheric haze. This position allows it to influence the weather patterns and cloud formations observed in the equatorial region. By capturing images in the near-infrared wavelength range, the James Webb Space Telescope can observe altitudinal layers with surprising clarity. These observations revealed several wind shears, which are areas where wind speed changes significantly with altitude or distance. These shears allowed researchers to track the motion of the jet stream effectively. The data was taken at 10-hour intervals, which corresponds to one Jovian day, providing a detailed snapshot of atmospheric changes over a single rotation. Additional observations from the Hubble Space Telescope taken one day after the data from the Webb telescope played a crucial role in determining the baseline of the equatorial atmosphere of Jupiter. While observations from Hubble focused on the lower layers visible to optical light, the near-infrared capabilities of the Webb telescope provided a detailed look at high-altitude features. This dual perspective allowed scientists to measure how wind speeds change with altitude and revealed the presence of significant vertical shifts. The detection of this specific jet stream was unexpected, as previous observations by ground-based telescopes and missions like Juno and Cassini had not revealed such detailed features. The researchers intend to continue observing Jupiter with the James Webb Space Telescope to determine if the speed and altitude of this newly discovered jet stream change over time. It is not enough to simply detect a feature. Understanding its stability is key to unlocking the atmospheric code of the planet. Lee Fletcher of the University of Leicester suggests that the strength of the new jet may be directly related to variations in the stratosphere of the planet. If this hypothesis holds true, the jet could change significantly over the next few years as the stratospheric conditions evolve. This ongoing study may reveal crucial information about the cyclical dynamics of the atmosphere of the gas giant, determining whether these features are permanent fixtures or transient phenomena driven by seasonal or multi-year cycles. While new discoveries are being made, the most famous feature of the planet is also under scrutiny. The Great Red Spot of Jupiter, the largest and oldest known storm in the solar system, has long been a subject of fascination and mystery. It is the defining characteristic of the planet, a crimson eye that has stared back at Earth for generations. However, recently new theories have emerged that challenge our fundamental understanding of this iconic atmospheric formation. These studies suggest that the Great Red Spot we observe today may not be the same storm observed by astronomers centuries ago. This challenges the romantic notion of a storm that has raged continuously for nearly 400 years. In the year 1665, the Italian astronomer Giovanni Cassini recorded a giant dark spot on Jupiter. He named this feature the permanent spot, believing it to be a fixed geographic feature on the cloud surface. This feature was perhaps first noted even earlier by the English scientist Robert Hooke in the year 1664. For decades, this spot was a reliable marker for early astronomers, allowing them to calculate the rotation speed of the massive planet. However, the historical record shows a significant gap. The spot disappeared from observations by the year 1713. For more than a century, no astronomer reported seeing this massive storm. It was not until the year 1831 that a similar feature was recorded at the same latitude. For many years, astronomers operated under the assumption that the permanent spot observed by Cassini was the same as the modern Great Red Spot, simply having gone through a period of low visibility or poor record-keeping. However, a recent comprehensive study led by Agustín Sánchez La Vega of the University of the Basque Country suggests otherwise. After analyzing the size and movement of these vortices over time and correlating them with historical drawings and modern data, the researchers concluded that it is highly unlikely that the current Great Red Spot is the same physical entity as the permanent spot of Cassini. The evolution of the storm morphology does not fit a continuous timeline. Most likely, The original storm observed in the 17th century dissipated and disappeared completely between the mid-18th and 19th centuries. This conclusion revises the biography of the storm, making the current Great Red Spot a younger formation, likely born in the mid-19th century, giving it a lifespan of more than 190 years rather than nearly 4 centuries. Using this historical data as a foundation, Sanchez La Vega and his team performed advanced computer modeling to figure out how the Great Red Spot might have formed if it is indeed a younger storm. The leading theory derived from these simulations is that wind instability in the atmosphere of Jupiter created an elongated atmospheric cell. This process involves a complex interaction between the high-speed zonal winds of the planet and the fluid dynamics of its dense atmosphere. The disturbance likely began as a long protostorm, which eventually contracted and spun up into the compact oval vortex we see today. One of the most significant and concerning observations of the Great Red Spot in the modern era is its constant shrinking. We are witnessing the decay of a giant in real time. In the year 1879, recorded measurements indicated that the size of the spot was about 24,200 miles along its longest axis. To put that in perspective, that is wide enough to fit 3 planets the size of Earth side by side. However, today, it is only 8,700 miles long. This is a dramatic decrease, representing a substantial loss of area and energy. This reduction in size raises profound questions about the future of the storm. Will the Great Red Spot eventually disappear, just as the permanent spot of Cassini did 3 centuries ago? The shrinking has changed the shape of the storm from a long cigar-like oval to a more circular form, which may impact its stability. The research team plans to conduct further modeling to predict the ultimate fate of the Great Red Spot. These models will help scientists understand whether the storm will eventually dissipate into the surrounding cloud bands, and if so, whether a new vortex could form in its place. It is possible that Jupiter undergoes a centuries-long cycle of storm generation and dissipation, where Great Red Spots are recurrent features rather than permanent ones. The study of the Great Red Spot not only deepens our knowledge of Jupiter, but also provides insight into the behavior of large-scale vortices on other gas giants, such as Saturn, Neptune, and Uranus, and even on exoplanets orbiting distant stars. This new perspective highlights the importance of continuous observations and advanced modeling in unlocking the mysteries of our universe. It demonstrates that even the most familiar features in the night sky are subject to change and reinterpretation. Despite the vast differences between Jupiter and Earth, the dynamics of their atmospheres and oceans reveal surprising similarities, proving that physics is universal. Recent research by physical oceanographer Leah Siegelman has shown that the gas cyclones of Jupiter mirror the behavior of oceanic structures on Earth, offering new insights into the underlying mechanisms that govern these powerful systems. This cross-disciplinary approach, treating a gas planet like a fluid ocean, has opened new avenues of understanding. The atmosphere of Jupiter is often described as an ocean of gas. Because the gas is under such immense pressure, it behaves fluid dynamically, much like liquid water does on Earth. It exhibits cyclonic activity, driven by convection, similar to storms and currents on our home planet. Convection is the process by which heat is transferred through fluid motion. On a planetary scale, it is the engine that drives weather. It plays an important role in both terrestrial and Jovian weather systems. On Earth, convection occurs in both the atmosphere, where it creates storm fronts, and in the oceans, where it drives global currents. A study by Siegelman, who analyzed high-resolution data from the NASA Juno spacecraft, has identified filaments which are wispy tendrils of gas located between the massive vortices of Jupiter. These filaments are not merely aesthetic details. They are functional components of the atmospheric engine. They behave similarly to fronts in the oceans and atmosphere of Earth. These fronts are characterized by boundaries between masses of different densities. On Earth, these boundaries are crucial to the generation of strong winds and currents. For example, a cold front pushes under warm air, creating energy and motion. On Earth, these density differences are usually due to variations in temperature and salinity in the ocean, or temperature and humidity in the atmosphere. On Jupiter, the mechanism is slightly different, but the principle remains the same. The density differences arise primarily from temperature differences in the gaseous layers. By calculating the horizontal and vertical wind speeds of these filaments using infrared images derived from the spacecraft, the team led by Siegelman confirmed that they contribute significantly to the energy dynamics of the cyclones of Jupiter. These filaments act as conduits, helping to transfer thermal energy from the hot interior of the planet to its upper atmosphere. This vertical transport accounts for a significant portion of the total kinetic energy of the cyclone and facilitates vertical heat transport. This explains why the storms on Jupiter can last for years or centuries. They are constantly being fed energy from below through these convective filaments. The presence of convection and fronts on both Earth and Jupiter suggests that these physical mechanisms are fundamental to turbulent fluid bodies throughout the universe. Whether it is water in the Atlantic Ocean or hydrogen and helium on Jupiter, the laws of fluid dynamics dictate the flow of energy. This finding implies that similar processes may exist on other planets with thick atmospheres or fluid layers, expanding our understanding of planetary science. If we can model the ocean of Earth, we can better model the atmosphere of Jupiter, and vice versa. The comparison of the gas cyclones of Jupiter with the oceanic structures of Earth provides a solid basis for the study of other celestial bodies. The ability to draw parallels between such different environments emphasizes the universality of certain physical principles, regardless of specific local conditions. The advances in our understanding of Jupiter, provided by the discoveries from the James Webb Space Telescope and the Juno mission, not only expand our knowledge of the planet, but also set new standards for what can be achieved with advanced space telescopes and probes. High-resolution images and detailed data have revealed previously unseen structures and dynamics in the atmosphere of Jupiter, moving us from low-resolution guesswork to high-precision science. These discoveries pave the way for future missions and exploration. Planned missions such as the Jupiter Icy Moons Explorer, or JUICE, led by the European Space Agency, will delve deeper into the Jupiter system. While previous missions focused heavily on the planet itself, JUICE will focus on its major moons, Ganymede, Callisto, and Europa. The purpose of these missions is to explore the potential habitability of these moons. These bodies are believed to harbor vast subsurface oceans beneath their icy crusts. By understanding the radiation and magnetic environment of Jupiter, researchers can better understand the conditions on these moons. The mission aims to further unravel the mysteries of the atmosphere of Jupiter and how it interacts with its satellites. Future space telescopes and probes will have more advanced sensors, enhanced data processing capabilities, and more sophisticated observational techniques. These tools will enable even more detailed and comprehensive studies of distant planets and their atmospheres, allowing us to see smaller features and measure subtler changes. By continuing to study the features of this gas giant and its similarities to our home planet, scientists will be able to better predict and model the behavior of the atmospheres of other planets. This comparative planetology is essential for the future of astronomy. As we discover more exoplanets, knowing how gas giants evolve and function will help us categorize these distant worlds. This will expand our knowledge of the cosmos and subsequently help in the search for habitable worlds. the journey is just beginning. While we continue to map the dynamic atmospheres of the planets within our own solar system, there is a phenomenon in the broader field of astronomy that has intrigued and puzzled scientists for decades. Hidden behind the glittering veil of the Milky Way in a specific region of space that astronomers refer to as the zone of avoidance, there exists a gravitational anomaly so vast and so powerful that it tugs at the very fabric of our local benign universe. This structure is known as the Great Attractor. Although it remains largely invisible to our standard optical telescopes, its gravitational influence is undeniable and profound, affecting the motion of galaxies hundreds of millions of light-years away, including our own Milky Way. The fundamental question remains: what exactly is the Great Attractor? Is it a supermassive black hole of unprecedented scale, a colossally dense cluster of galaxies, or something else entirely? More importantly, what does its existence mean for us, for the trajectory of our galaxy, and for the future evolution of the local universe? To understand this, we must explore the impact of the Great Attractor on our galaxy and the immense technical challenges scientists face in observing this elusive region of the cosmos. We must also examine the recently discovered South Pole Wall, a vast filament of galaxies stretching at least 700 million light-years into space, and investigate its intriguing connection to the Great Attractor. The question of whether we will eventually be consumed by this anomaly, or if it serves another structural purpose in the grand scheme of the universe, drives much of modern extragalactic astronomy. About 4 decades ago, astronomers utilized the Parkes Observatory radio telescope to peer through the obscuring dust of the Milky Way. What they discovered was startling. Our galaxy is traveling through space much faster than could be explained by the standard expansion of the universe alone. Imagine for a moment the sheer scale of this velocity. Our Milky Way is traveling through intergalactic space at a speed 2,500 times the cruising speed of a commercial airliner. This is 55 times the escape velocity required to leave the Earth, and twice the escape velocity required to escape the gravitational pull of the Milky Way galaxy itself. But where does such tremendous movement come from? This presents a significant mystery in cosmology. The theory of our origin based on the Big Bang model dictates that on large scales, every point in the universe should be flying apart from every other point as space itself expands. This is known as the Hubble flow. According to this rule, galaxies on either side of us should be moving away at the same recessional velocity, which should not result in any net motion in the reference frame of the Milky Way. However, we observe a clear deviation from this smooth expansion. Net motion, or what astronomers call peculiar velocity, can arise from the gravitational influence of nearby clusters or irregularities in the distribution of matter. For instance, a massive cluster of galaxies creates a gravity well. The additional gravitational attraction of such a cluster can slow down and in its immediate vicinity even reverse the expansion of the universe, pulling neighboring galaxies toward it. However, when astronomers looked in the direction of the motion of the Milky Way, such a cluster was not immediately obvious. There is indeed an excess of galaxies in the general vicinity, and an excess of radiation visible in X-ray telescopes, indicating high-energy gas. Yet, initially, nothing appeared large enough to mathematically explain the extreme speed of our galaxy. This led to 2 possibilities. Either we are observing a superdensity of pure dark matter, which exerts gravity but emits no light, or the current theory of the origin of mass and motion is fundamentally flawed. Astronomer Alan Dressler of the Carnegie Institution supported the first explanation. He famously coined the term Great Attractor to describe this missing concentration of matter. Despite the catchy name, the mystery of the Great Attractor continues to baffle the scientific community. Despite our best efforts and the discovery of new galaxies, galaxy clusters, and new filaments in the cosmic web, we still have not found enough visible matter to fully account for our motion. The Great Attractor remains a partially solved puzzle pulling in our Milky Way, and leaving us with significant questions about the mass distribution of the local universe. So over a vast expanse of space, some 220 million light-years away, lies this gravitational anomaly. It is important to clarify that the Great Attractor is located within the Laniakea supercluster, the massive structure that contains our own local group of galaxies. This region has such an enormous gravitational pull that it dictates the flow of the universe in our corner of the cosmos. But what is a Great Attractor physically? The term was coined to describe its function rather than its form. It is not actually a single monolithic entity like a black hole, but rather a diffuse yet massive region of space with a significantly higher concentration of mass than the universal average. This mass consists not only of visible matter like stars, galaxies, and gas clouds, but also dark matter. Dark matter is an invisible and mysterious form of matter that interacts only through gravity and by some estimates makes up about 85% of the total mass of the universe. Therefore, when we look at the Great Attractor, we are seeing the gravitational footprint of a massive dark matter halo filled with thousands of galaxies. Understanding the Great Attractor is like putting together a cosmic puzzle where half the pieces are missing. We know it is there because we can observe its gravitational effects. We see galaxies streaming toward it, like water flowing down a drain. However, we cannot see it directly because it is located in the zone of avoidance. This is a region of the sky that is obscured by the plane of our own Milky Way galaxy. The disk of our galaxy is filled with thick clouds of interstellar dust and gas and billions of bright stars. This acts as a curtain, blocking the view of the universe beyond. It is equivalent to trying to see a distant mountain range while standing in the middle of a dense fog bank. Despite these challenges, scientists have made significant progress in studying the Great Attractor. They have moved beyond optical telescopes which are blocked by dust and have used various techniques such as X-ray, infrared, and radio observations. These wavelengths of light can penetrate the dust and gas of the Milky Way, allowing us to gain insight into this mysterious region of space. According to information gathered to date, the Great Attractor is likely the center of a larger structure called the Norma Cluster. The Norma Cluster is one of the most massive and dense galaxy clusters known to science. It is in this cluster that the dynamical center of the Great Attractor is located. The Norma Cluster itself is moving toward the core of the Great Attractor at an astounding speed of about 1,340 meters per second, relative to the cosmic microwave background. As we have noted, the gravitational influence of the Great Attractor extends over a region of space spanning hundreds of millions of light-years. This region, known to us as the gravity well of the Great Attractor, acts as a basin of attraction. It includes our own local group of galaxies, which is being pulled toward the Great Attractor at a rate of about 370 miles per second. This speed is superimposed onto the general expansion of the universe, creating the complex flow patterns we observe today. Observing the Great Attractor is not easy. One cannot simply point a standard optical telescope at it and record an image. The main problem is its location relative to our vantage point on Earth. The Great Attractor is located directly behind the center of the Milky Way, in the heart of the zone of avoidance. This zone covers about 20% of the sky and is opaque to visible light. The density of dust and stars here creates a foreground that overwhelms faint signals from the distant universe. However, this has not stopped astronomers from trying to unlock its secrets. They have to be creative in their methods, using different types of observations to peer through the dust and gas of our own galaxy. One of the main methods used is the observation of the 21-centimeter neutral hydrogen line. This is a specific wavelength of radio waves emitted by neutral hydrogen atoms, which are the most abundant element in the universe. To understand why this is effective, we must look at the atomic physics involved. A hydrogen atom consists of one proton and one electron. When the spin of the electron flips from being parallel to the spin of the proton to being anti-parallel, it emits a photon with a wavelength of exactly 21 centimeters. This is a radio wave, not visible light. The distinct advantage of using radio waves is that they have a much longer wavelength than visible light. This allows them to pass right through the microscopic dust grains in the Milky Way without being scattered or absorbed. While the dust blocks visible starlight, it is transparent to the 21-centimeter radio signal. This makes the galaxy effectively invisible in this part of the spectrum, allowing astronomers to see what lies behind it. In the late 1990s, a group of astronomers began using the Parkes multi-beam receiver, an innovative instrument located in New South Wales, Australia. Before this technology, telescopes had to scan the sky one single point at a time, which was incredibly time-consuming. The multi-beam receiver, however, was a game-changer. It allowed the telescope to observe 13 distinct points in the sky, simultaneously vastly increasing the speed and efficiency of the survey. This receiver's unique sensitivity and wide field of view allowed for increasingly sensitive radio surveys of the southern sky where the Great Attractor is located. These surveys did not rely on seeing the light from stars, but rather detected the radio hum of the hydrogen gas contained within galaxies. These blind surveys detected thousands of galaxies that were previously completely hidden from view. These radio data, when combined with data from new infrared surveys by the Hubble Space Telescope, have allowed astronomers to confirm the presence of nearly 80% of the galaxies predicted to exist in the zone of avoidance. Infrared light, like radio waves, penetrates dust better than visible light, helping to complete the picture. However, the work is not finished. The remaining 20% of the predicted mass lies in the very densest part of the galactic plane. These galaxies are too deep in the Milky Way to be confirmed with any existing optical or infrared telescopes. The zone of avoidance is a fascinating and frustrating region of space. It acts like a heavy velvet curtain that hides a significant portion of the extragalactic universe from our view. However, with the help of advanced technology and innovative techniques, we have been able to peek behind this veil to see the hidden galaxies that populate the void beyond. While radio waves allow us to track the gas content of these galaxies, the use of infrared surveys has been equally crucial in mapping their stellar populations. These surveys have allowed astronomers to confirm the presence of galaxies that were previously invisible to optical telescopes. Infrared light has a longer wavelength than visible light, which allows it to pass through the dense clouds of interstellar dust much more effectively. It is like having a powerful torch that can illuminate the dark corners of the universe, revealing the structural skeleton of the cosmos that was once obscured by our own galactic foreground. As we continue to explore and map the local universe, a colossal structure known as the South Pole Wall has been discovered in the vast expanse of space deep within the southern celestial hemisphere. This wall is a dense filament composed of thousands of galaxies, along with vast amounts of dust and gas. It extends for at least 700 million light-years across the sky. To grasp the magnitude of this figure, the entire Milky Way galaxy is only about 100,000 light-years across. The South Pole Wall is so massive that its gravitational mass disrupts the local expansion of the universe, creating a distinct flow pattern in the galaxies around it. However, this huge structure, like the Great Attractor, remains largely hidden behind the plane of our galaxy. The Milky Way blocks our direct line of sight, making visual identification nearly impossible. Spatially, it stretches from the constellation Perseus in the northern hemisphere all the way to the constellation Apus in the far south, forming a massive arc that wraps around our region of space. Despite its immense proximity and size, it has long gone unnoticed, sitting silently in a darkened sector of the southern sky. The South Pole Wall is a recent discovery announced by an international team of astronomers led by Daniel Pomerede of the University of Paris-Saclay and R. Brent Tully of the University of Hawaii. These researchers are pioneers in the field of cosmography, which is the science of mapping the universe. The discovery was made possible not by seeing the wall directly, but by measuring the distances and motions of 18,000 galaxies, located up to 600 million light-years away. This technique relies on detecting the gravitational influence of the invisible mass. Although the South Pole Wall is not visible to us in standard images, we can observe its gravitational signature in the peculiar velocities of the surrounding galaxies. In an expanding universe, distant galaxies naturally fly away from us according to the Hubble law. This is the baseline expansion rate. However, gravity from massive structures causes deviations from this smooth flow. Galaxies located between Earth and the South Pole Wall are moving away from us a little faster than they should be, based on cosmic expansion alone. This is because they are being drawn outward by the huge clump of matter in the wall, effectively adding speed to their recession. Conversely, galaxies located beyond the wall move outward more slowly than expected because they are being held back by the gravitational resistance of the wall, pulling them in the opposite direction. By mapping these subtle changes in speed, researchers could mathematically reconstruct the shape and density of the wall without ever seeing it directly. The South Pole Wall is an important architectural component of our local universe. In terms of scale, it is as large as the Sloan Great Wall, which was previously one of the largest known structures in the cosmos. However, the South Pole Wall is twice as close to us as the Sloan Great Wall, making its gravitational impact on us much more significant. However, it still goes unnoticed by the casual observer because of its hidden location in the southern part of the sky, obscured by the galactic center. It is connected to the larger structure of the Laniakea supercluster, which is the home structure that contains our own Milky Way and the Great Attractor. All these structures are interconnected, forming a vast cosmic web of filaments and voids. They collectively affect the local expansion of the universe and dictate the motion of the galaxies within them. The Great Attractor, the South Pole Wall, and other such massive structures shed light on another enduring cosmic mystery, which is the question of where we are going. Imagine you are floating down a river in a small boat without oars. The current of the river guides the motion of your boat. This current represents the gravitational pull of these cosmic structures. No matter how hard you might try to control your boat, the pull of the current is too great, ultimately determining your path and speed. Similarly, our galaxy is like a small boat in a cosmic river. We are moving at nearly 1.3 million miles per hour, guided by the gravitational pull of massive structures such as the South Pole Wall and the Great Attractor. We are not drifting aimlessly. We are flowing toward a specific destination, dictated by the distribution of matter in the local universe. The future of our understanding of the universe and the true nature of the Great Attractor lies in further research and more precise mapping. Astronomers from Australia are leading several pioneering projects to refine these maps. The 2MTF survey, initiated by the Centre for All-Sky Astrophysics, has already made significant progress using the Parkes Radio Telescope. This survey calculates precise distances to galaxies, shedding light on the structure and motions in our neighboring universe. But the research does not end there. The upcoming Wallaby study, due to begin fully later this year, promises to push the boundaries of our understanding even further. This survey utilizes the Australian Square Kilometre Array Pathfinder, or ASKAP telescope. This is a next-generation radio telescope located in Western Australia. The Wallaby survey will allow us to probe deeper into the radio universe, detecting the neutral hydrogen signatures of galaxies that are too faint for current instruments. In tandem with these radio surveys, the Australian Astronomical Observatory and the Australian National University are embarking on a new optical survey called Taipan. While radio surveys look at gas, Taipan will focus on measuring the distances to elliptical galaxies. Elliptical galaxies are old, massive systems that serve as excellent standard markers for cosmic distance. This project allows us to travel mathematically to more distant regions of the universe, refining our map of the velocity field. As research continues, our fundamental understanding of the universe is being challenged. Theorists are beginning to question the validity of the space-time metric we currently use to describe the universe. If the observed flows of galaxies do not perfectly match the distribution of visible mass, it could imply that our understanding of gravity on these massive scales is incomplete. There is even talk in the scientific community of the need to modify the general theory of relativity on large scales to account for these discrepancies. As we look out into the cosmic expanse, we cannot help but ponder the ultimate future of our universe. What does the accelerated expansion of the universe due to dark energy mean for us, for the Milky Way, for our great attractor, and for the countless galaxies dotting the cosmic landscape? The universe is not static. It is expanding. Furthermore, this expansion is being accelerated by a mysterious force called dark energy. This force acts as a repulsive pressure on the vacuum of space itself. It is so powerful that it stretches the very fabric of space-time, causing galaxies to diverge from each other at increasing speeds. But what does this mean for the future of galaxies on superscales? And what role does the Great Attractor play in this cosmic drama? Despite the relentless expansion of the universe, the Great Attractor continues to exert a powerful gravitational influence on the galaxy clusters surrounding it, including our Milky Way. This creates a cosmic tug-of-war. Gravity tries to pull things together, while dark energy tries to push them apart. So back to the burning question: will the Great Attractor eventually swallow us up? The answer, based on current cosmological models, is no. Despite its enormous gravitational pull, the Great Attractor is not a cosmic monster ready to swallow us whole. We are moving toward it, but the space between us is also expanding. As the universe expands, the relative influence of gravity over vast distances will weaken compared to the accelerated expansion driven by dark energy. In the distant future, as the expansion of the universe continues to accelerate, galaxies that are currently attracted to the Great Attractor may begin to move away from it. The gravitational bonds holding the superclusters together will eventually be overcome by the repulsive force of dark energy. These massive structures may begin to disintegrate and fragment. The future of the universe is a vast, ever-expanding cosmic sea. Galaxies will become like isolated islands drifting in the cosmic ocean, slowly moving away from each other until they disappear from view. The Great Attractor, once a formidable gravitational anchor, will eventually lose its power over the galaxies around it. The local groups will remain bound by their own strong internal gravity, but the large-scale structures will dissolve into the void. From the vast structures of the cosmos, we turn our attention to one of the oldest and most profound questions humanity has ever asked. Are we alone in the universe? For centuries, this question belonged to the realm of philosophy and science fiction. But recent technological advancements have moved it firmly into the domain of observational science. The James Webb Space Telescope, or JWST, may have just brought the scientific community one step closer to a revolutionary discovery. The focus of this intense scrutiny is a distant exoplanet known as K2-18b. This remote world has suddenly found itself at the forefront of astrobiological research. The reason for this attention is that the Webb telescope has discovered something unusual in its atmosphere. It has detected chemical signatures that could potentially signal the existence of biological processes. The data indicates the presence of water vapor, methane, and potentially a molecule known as dimethyl sulfide. In the search for extraterrestrial life, these are not just random molecules, they are potential biosignatures. A biosignature is a substance that provides scientific evidence of past or present life. Armed with the most advanced space technology ever created, the James Webb Space Telescope acts as a guardian of scientific discovery, designed to peer into the unknown and perhaps redefine the understanding of life itself. To understand the significance of these findings, we must venture into the mysterious world of K2-18b and understand the tools used to observe it. As researchers venture deeper into space in search of answers, they rely on the eyes of technological marvels to bring the universe into focus. For decades, the Hubble Space Telescope was the primary window to the universe, producing images that delighted and enlightened the public. However, even a tool as powerful as Hubble has its limitations, specifically regarding the wavelengths of light it can capture. James Webb represents the next generation of observation dedicated to pushing the boundaries of what is visible. One of the most innovative and critical features of the JWST is its cooling technology, specifically its sunshield. This is no ordinary sunshade. It is a multi-layered engineering marvel, the size of a tennis court, designed to block the intense heat and light from the sun, earth, and moon. This thermal protection is vital because the telescope is optimized for infrared light. Infrared light is essentially heat radiation. If the telescope were not kept at incredibly low temperatures, roughly minus 370 degrees Fahrenheit, the heat from its own instruments would blind it to the faint signals from deep space. This extreme cooling increases the sensitivity of the telescope to the faint infrared signals emitted by distant celestial bodies. Infrared observations are crucial for studying exoplanets such as K2-18b. Unlike visible light, which can be easily absorbed or scattered by space dust and thick planetary hazes, infrared waves have longer wavelengths that can penetrate these obstacles. This capability gives scientists clearer and more detailed data about the chemical composition of atmospheres that would otherwise be opaque. The ability of the Webb telescope to make these high-precision infrared observations is not just an incremental achievement, it is a fundamental revolution in the way astronomers study distant worlds, allowing for the detection of specific molecules based on how they interact with light. So what specific discoveries await when this powerful gaze is turned toward K2-18b? This exoplanet is located 124 light-years away from Earth in the constellation Leo. In cosmic terms, this is a relatively close neighbor. K2-18b is more than just a distant rock. It orbits a red dwarf star named K2-18. Crucially, it orbits within the habitable zone of its star, often referred to as the Goldilocks zone. This is the specific region around a star where conditions are theoretically ideal, neither too hot nor too cold for liquid water to exist on the surface of a planet. However, simply being in the habitable zone does not guarantee life. What sets K2-18b apart from other exoplanets in similar orbits is its classification. It is not a gas giant like Jupiter, nor is it a small rocky world exactly like Earth. It is what scientists call a Haitian world. The term Haitian is a combination of the words hydrogen and ocean. These worlds are characterized by a massive hydrogen-rich atmosphere and a surface likely covered by a global liquid water ocean. This represents a new frontier in the search for extraterrestrial life. Haitian worlds are generally larger than Earth, but smaller than Neptune, often referred to as sub-Neptunes. The conditions on these worlds may be similar to those found around hydrothermal vents in the oceans of Earth, which are known to support diverse and resilient ecosystems despite the lack of sunlight. Recent observations by the James Webb Space Telescope, utilizing its near-infrared imager and slitless spectrograph, and near-infrared spectrograph have revealed intriguing details about the atmosphere of K2-18b. The spectral data shows a chemical cocktail that includes carbon-bearing molecules such as methane and carbon dioxide. The detection of methane and carbon dioxide and the notable shortage of ammonia supports the hypothesis that there may be a water ocean underneath a hydrogen-rich atmosphere. But the most provocative finding is the potential trace of dimethyl sulfide. On Earth, dimethyl sulfide is a molecule produced almost exclusively by life. The bulk of it in the atmosphere of Earth is emitted from phytoplankton in marine environments. This has caused a wave of excitement in the scientific community. However, researchers remain cautious. The signal for dimethyl sulfide is not as strong as the signals for methane or carbon dioxide, and further observation is required to confirm its presence. Researchers are full of excitement and speculation as they ponder the implications of these discoveries for astrobiology. If confirmed, the presence of dimethyl sulfide, combined with methane and carbon dioxide, would be a strong indicator of biological activity. Could this Haitian world, with its unique atmospheric composition, be the key to unlocking the mysteries of extraterrestrial life? When scientists venture into the field of exoplanet exploration, one of the most challenging but rewarding aspects is the study of alien atmospheres. K2-18b, with its unique location and intriguing composition, provides a compelling case study. While the atmosphere of Earth is a mixture primarily of nitrogen and oxygen, with trace gases, K2-18b presents a very different chemistry. Its hydrogen-dominated atmosphere suggests a strong greenhouse effect which could keep the planet warm enough for liquid water, even if it receives less energy from its star than Earth does from the Sunday. This exoplanet is a treasure trove of scientific curiosities. Studying the atmosphere of a planet more than 100 light-years away is not an easy task. It involves a technique called transmission spectroscopy. This method analyzes the light from the parent star as it passes through the atmosphere of the planet during a transit event which occurs when the planet passes directly in front of the star from the perspective of Earth. As the starlight filters through the planetary atmosphere, different molecules absorb light at specific wavelengths. This creates a spectrum with dark gaps similar to a barcode. By decoding this barcode, scientists can determine which gases are present. The infrared capabilities of the James Webb Space Telescope played an important role in these discoveries. The mid-infrared instrument allows for an extended range of wavelengths, allowing detectors to identify a variety of molecules that were previously elusive to older telescopes. The presence of methane and the lack of ammonia in the atmosphere of K2-18b is particularly significant. On Earth, methane is often produced by biological processes, specifically by microorganisms known as methanogens. These organisms produce methane as a metabolic byproduct in low oxygen conditions. The presence of methane in a hydrogen-rich environment opens up the possibility of life forms that thrive in conditions vastly different from the surface of Earth. Furthermore, the chemical composition suggests that the ocean of K2-18b is likely not boiling away, but remains stable. This opens up exciting questions about atmosphere-ocean interactions. Just as the oceans on Earth absorb carbon and regulate the climate, the global ocean of a Haitian world would play a critical role in maintaining habitability. The dynamics of how gases exchange between the liquid ocean and the hydrogen atmosphere could affect the overall stability of the climate. So could this atmosphere be the key to a new understanding of habitability? When we think of life, we often bias our imagination toward Earth-like environments with green forests and blue skies. But in fact, life exists in environments where we can hardly imagine survival. To understand what might live on K2-18b, scientists look to extremophiles on Earth. Extremophiles are organisms that thrive in extreme environments that would be lethal to humans. Studying them opens up new possibilities for understanding life beyond Earth. Deep in the oceans of Earth, along the tectonic plate boundaries, hydrothermal vents spew hot mineral-rich water into the freezing darkness. These environments are devoid of sunlight and are subjected to immense crushing pressure, yet they are teeming with life. In these ecosystems, the food chain is not based on photosynthesis from the sun, but on chemosynthesis. Bacteria convert the chemicals from the vents, such as hydrogen sulfide, into energy. Extremophiles, such as thermophiles, which love heat, and acidophiles, which thrive in acidic conditions, challenge the traditional understanding of the limits of life. Could similar life forms exist on exoplanets like K2-18b? The hydrogen-rich atmosphere offers unique conditions for metabolism. On Earth, certain microbes called methanogens produce methane in an oxygen-free environment by consuming hydrogen and carbon dioxide. This is a very efficient way to gain energy in an environment where oxygen is scarce. If the methane in the atmosphere of K2-18b is indeed produced biologically, it implies we may be looking at a world where hydrogen-loving extremophiles are the dominant form of life. The study of extremophiles expands the range of conditions in which biologists believe life can exist. From the acidic red rivers of Rio Tinto in Spain, which mimic the chemistry of Mars, to the frozen tundra of Siberia, where microbes survive in permafrost, life on Earth demonstrates incredible adaptability. This diversity encourages the scientific community to reconsider the ecological limits of extraterrestrial life. The potential for a subterranean ocean and a hydrogen-rich atmosphere makes K2-18b an attractive target for studying extremophiles in the exoplanet environment. Perhaps this distant world has evolved its own version of extreme life, adapted to such specific conditions, involving high pressure and hydrogen metabolism. If extremophiles do indeed exist on K2-18b, we must ask what their evolutionary trajectory might look like. On Earth, life began with simple, single-celled organisms, and over billions of years evolved into complex multicellular forms. This progression required not just time, but also environmental stability. Could a similar process occur on other worlds given enough time and the right chemical ingredients? One of the most interesting and debated aspects of studying the atmosphere of K2-18b is the potential presence of dimethyl sulfide, or DMS. On Earth, this organic compound is produced almost exclusively by life, specifically by marine phytoplankton. It serves as a primary potential biosignature because there are no known geological processes that produce it in significant quantities. But could its presence on an exoplanet like K2-18b also indicate a thriving biosphere? To answer this, we must look at the function of the molecule here at home. In the oceans of Earth, DMS is not just a waste product. It serves many ecological functions. It is a compound that, when released into the air and oxidized in the atmosphere, aids in the formation of cloud condensation nuclei. This leads to cloud formation, which reflects sunlight and cools the planet. This feedback loop, known as the Claw hypothesis, suggests that biology actively regulates the climate of a planet. Its presence in an exoplanet atmosphere such as that of K2-18b could be a game changer in the search for extraterrestrial life, because it suggests that life might be modifying the planetary environment on a global scale. However, the potential detection of DMS on K2-18b is still being rigorously tested. The mid-infrared instrument of the James Webb Space Telescope is capable of detecting such complex molecules, but the signal is incredibly faint. Confirming its presence requires careful analysis and expert judgment to separate the signal from the background noise of the star and the instrument itself. The discovery of potential biosignatures such as DMS at K218b has rightfully excited the scientific community. However, like any groundbreaking discovery, it has also sparked a debate that oscillates between skepticism and optimism. The scientific community is currently divided on the implications of the discovery. While some consider it a strong candidate for biosignatures, others warn that abiotic processes, non-biological chemistry, could potentially produce similar compounds under the high-pressure and hydrogen-rich conditions of a Haitian world, which are very different from Earth. This debate emphasizes the complexities and challenges in interpreting exoplanet data. Historically, astronomical discoveries have often been met with skepticism, which serves as a necessary filter for truth. When Galileo Galilei first discovered the satellites of Jupiter in the 17th century, his findings were initially rejected by many contemporaries because they challenged the established geocentric view of the universe. Similarly, the discovery of the first exoplanet, orbiting a sun-like star in the year 1995, was met with extreme caution until it could be independently verified. These historical examples serve as a reminder that skepticism is an integral and healthy part of the scientific process. It prevents us from jumping to conclusions based on desire rather than data. The search for extraterrestrial life does not depend on a single molecule or a single observation. Scientists are looking for a combination of biosignatures to create compelling evidence for the existence of life. This is often referred to as a disequilibrium state. On a dead planet, chemicals settle into a balanced state. On a living planet, biology constantly replenishes unstable gases. Could DMS be a part of a larger puzzle involving other biosignatures like methane and water vapor, appearing together in a way that geology cannot explain? The debate is likely to continue until additional data is collected. As technology advances, future missions with even more sensitive instruments may provide the confirmation needed to classify DMS as a true biosignature. Is DMS the key we have been waiting for in the search for alien life? Or is it a distraction that is throwing us off track by mimicking biology? Either way, the debate itself is a testament to the ever-evolving nature of scientific research, where every answer leads to new questions. The James Webb Space Telescope has revolutionized our understanding of exoplanets like K218b, but it is just one step in a long journey of space exploration. What lies beyond this monumental mission? And how will future technologies continue to expand our cosmic horizons? We are entering a golden age of observational astronomy. The Extremely Large Telescope, or ELT, led by the European Southern Observatory, is scheduled for completion around the year 2025. It promises to be another game changer. Located in the Atacama Desert of Chile, it represents the pinnacle of ground-based astronomy. With a main mirror diameter of nearly 128 feet or 39 meters, it will be the largest near-infrared and optical telescope in the world. Its unprecedented sensitivity and angular resolution will allow it to gather more light than all existing major research telescopes combined. It could confirm or refute the biosignatures detected by the James Webb Space Telescope by analyzing the light of exoplanets with even greater spectral resolution. While ground telescopes grow larger, space missions are becoming more specialized. The Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, is another mission concept on the horizon that could complement the findings of the James Webb Telescope. Designed to operate over a wide range of wavelengths, including ultraviolet, which Webb does not see, LUVOIR would provide even more detailed atmospheric analysis. Crucially, it aims to potentially obtain direct images of Earth-like exoplanets. Currently, we mostly study these planets indirectly as they pass in front of their stars. Direct imaging would allow us to see them as distinct points of light. separating the pale blue dot from the glare of its sun. This would allow for the analysis of surface features and seasonal changes. As we target more distant exoplanets beyond our immediate neighborhood, advances in propulsion technology will become critical components of exploration. While telescopes allow us to look, getting physical probes to these worlds remains a challenge for the distant future. Current chemical rockets are far too slow for interstellar travel. Advanced concepts like ion propulsion, which uses electric fields to accelerate ions, are already in use and offer great efficiency but low thrust. Theoretical methods involving antimatter propulsion could drastically reduce travel times. Antimatter-matter annihilation releases the maximum possible energy according to the laws of physics. If harnessed, it could allow probes to reach and study exoplanets within a human lifetime rather than thousands of years. We have previously published a detailed discussion on the possibility of interstellar travel and the immense engineering challenges associated with it, but it remains the ultimate long-term goal of our species. As we stand on the threshold of potentially revolutionary discoveries, it is worth pausing to consider the philosophical implications and questions that fuel our cosmic curiosity. What does the search for extraterrestrial life mean for our understanding of existence, and what questions does it pose for the future of humanity? If we find life, it ends our cosmic isolation. If we do not, it highlights the precious fragility of our own existence. One question that is becoming increasingly relevant is the role of red dwarfs in the galaxy. Stars like K218 are red dwarfs, the most common type of star in the Milky Way. Could these numerous stars, often overlooked because of their small size and dim light, actually be the primary cradle of life in the universe? Their longevity is a key factor. While our sun will burn out in a few billion years, red dwarfs can burn for trillions of years, providing a stable environment for an immense period of time. This stability makes them intriguing candidates for planets that have life. However, they are also prone to violent solar flares, which could strip the atmospheres of orbiting planets. This presents a paradox, known as the red dwarf problem. Understanding whether life can survive around these stars is statistically vital to estimating the number of civilizations in the galaxy. What would the discovery of extraterrestrial phytoplankton or simple microbial life mean for our understanding of biology? Such a discovery would not only confirm the existence of life beyond Earth, but would also suggest that the building blocks of life are more universal than we thought. It would imply that biology is not a miracle, but a probable outcome of physics and chemistry. What will the next decade reveal in our quest to understand the cosmos? Will we confirm the existence of extraterrestrial life finding neighbors in the star systems next door? Or will we discover new, even more complex questions that challenge our understanding of the universe? The answers await us in the data. While we scan the skies for biological signatures on distant exoplanets, we are also forced to look backward in time to the very moment existence began. According to the Standard Model of Cosmology, approximately 13.8 billion years ago, a singularity arose. This was an entity of infinite density and infinite gravity, contained within a space smaller than a single atom. In a fraction of a second, this point swelled and cooled, giving birth to our universe. This event is known to us as the Big Bang. It was not an explosion in space, but an explosion of space itself. As the universe expanded, energy condensed into matter, eventually forming the stars and galaxies we observe today. However, speculation about such things does not provide definitive answers, but only generates more and more questions. The most persistent of these is simple yet profound. What was there before the Big Bang? Is there even a concept of before in a universe where time itself was born out of this primordial explosion? If time is a property of our universe, then asking what happened before it might be logically invalid. Yet the human mind craves causality. We ask if we are the first universe, or merely the latest chapter in an endless cycle of cosmic death and rebirth. The greatest minds of our species, including Albert Einstein, Stephen Hawking, and Roger Penrose, have proposed theories each as mind-boggling as the next to answer this. Some speak of other universes existing alongside our own, while others postulate a universe that breathes, collapses, and expands in an infinite cycle. Let us try to make sense of what actually happened before the beginning of time itself by examining the competing models of cosmic origin. Imagine a universe that behaves like a living lung. It expands outward from one single point, grows for billions of years, allowing stars and life to flourish, and then shrinks, drawing in all matter and energy back to the source. This is the essence of the oscillating universe theory, often referred to as the cyclic model. This model assumes that our universe is just one phase in an endless cycle of expansion and contraction, a cosmic dance that has neither a true beginning nor a definitive end. In this scenario, history repeats itself eternally. Each cycle begins with a Big Bang, an explosive moment of creation followed by a long period of expansion. Over billions of years, the gravitational pull of all the matter in the universe acts as a brake. Eventually, this expansion slows, stops, and then reverses. The universe begins to contract. Galaxies act like stones thrown into the air that eventually lose their upward momentum and fall back down. This contraction leads to the Big Crunch. During this terrifying phase, galaxies collide, stars are compressed, and the temperature of the cosmos rises exponentially. All matter and energy is squeezed back into a singular point of infinite density, very similar to the singularity from which the Big Bang occurred. But in the oscillating universe model, this is not the ultimate end. It is the catalyst for the next beginning. The intense pressure and heat trigger a big bounce. The singularity explodes with another Big Bang, starting the next iteration of the universe with a new timeline and potentially new physical properties. The lifetime of each universe in this model could be billions or even trillions of years, and each Big Bang prepares the ground for the next Big Bang. It is a fascinating concept. It essentially solves the problem of origin by claiming existence is eternal, appearing like a cosmic pendulum swinging back and forth between expansion and contraction, destroying and recreating universes in its path. However, the theory of an oscillating universe is not without flaws and significant criticisms. The primary issue is the second law of thermodynamics, which states that entropy or disorder always increases. If the universe cycles endlessly, entropy should build up with each cycle, making each subsequent universe longer and larger than the last until the cycle breaks. Furthermore, we have yet to understand many factors concerning the expansion of the universe, specifically its exact energy composition. Current data presents a major hurdle for the oscillating universe. Observations of Type 1a supernovae and the cosmic microwave background indicate that the expansion of the universe is not slowing down due to gravity. Instead, it is speeding up. This acceleration is driven by a mysterious force known as dark energy. If dark energy continues to dominate, the universe will not contract into a big crunch, but will expand forever, eventually suffering a heat death, where all energy is evenly distributed and life becomes impossible. The data points to an ever-accelerating expansion, not a possible future contraction. But as always, science continues to evolve. Our understanding of dark energy is less than 30 years old. Once rejected, theories might find new life in the light of new discoveries or modifications to our understanding of gravity. Throughout our exploration of space and time, we have always thought of our universe as unique. We view it as a single, isolated bubble of reality floating in an endless sea of nothingness. But what if we are not alone in a much grander sense? What if our universe is just one of an unimaginable multitude of other universes, each with its own laws of physics, its own history, its own beginning and end? This is the premise of the multiverse theory. This idea often stems from the theory of eternal inflation. Inflation suggests that immediately after the Big Bang, space expanded exponentially fast. If this inflation stops in some places, but continues in others, it creates isolated bubbles of stable space. Imagine a vast cosmic ocean of expanding energy in which countless bubbles appear and disappear. Each of these bubbles represents an independent universe, and our universe is just one of them among this cosmic foam. In this framework, some of these universes may be radically different from ours. They might have different physical constants. For example, the force of gravity might be stronger, or the speed of light might be slower. In such universes, stars might burn out in minutes, or atoms might never form at all, rendering life impossible. Others may be strikingly similar to our own, and may even contain life as we know it. This theory helps solve the fine-tuning problem, which asks why the constants of our universe are so perfectly set to allow for biology. In a multiverse with infinite variations, it is inevitable that at least one universe would have the right conditions for us to exist. We are simply in the one that allows us to be here, to observe it. But the implications go further. What if some of these universes preceded ours? Could our Big Bang have been caused by an interaction with another universe? Some theorists propose that a collision between two branes or membrane universes in a higher dimensional space could trigger the energy release we perceive as the Big Bang. The multiverse concept challenges our understanding of our place in the cosmos, demoting our universe from the entirety of existence to a mere speck in a larger ensemble. Nevertheless, it is a theory that remains highly speculative. While the multiverse theory is fascinating and mathematically viable within string theory, it is also controversial. The core requirement of science is testability. After all, if these other universes are beyond our reach and causally disconnected from us, how can we detect or study them? If the theory cannot be tested or falsified, can it be considered scientific, or does it drift into metaphysics? Nevertheless, multiverse theory continues to be the subject of research and debate among physicists. It represents the edge of our understanding, where science mixes with philosophy and observable facts give way to profound questions about the nature of reality itself. And yet, despite the supposed multiplicity of universes with all their variety of physical forces and dimensions, let us return to the realities of ours. To understand the origin, we must look at the tools we use to describe it. Our understanding of the universe rests on two pillars of modern physics. The first is quantum mechanics, which describes a world on the atomic and subatomic scale. It deals with probabilities, uncertainty, and particles that can be in two places at once. The second is general relativity, developed by Albert Einstein, which describes a world of very large dimensions like stars, galaxies, and the cosmos itself. But what happens when these two worlds collide? They are like two different languages that cannot translate into one another. According to the general theory of relativity, space and time are not a static stage, but are interwoven into a four-dimensional fabric known as space-time. Massive objects distort this fabric, creating what we perceive as gravity. A planet orbits a star because it is following a curve in space-time. On the other hand, quantum mechanics presents a world in which particles can exist in several states simultaneously, appearing and disappearing in a foam of quantum fluctuations. It is a world that challenges our everyday logic and assumes space is discrete rather than smooth. These two theories work perfectly well in their own domains. However, they meet in a catastrophic clash at the singularity of the Big Bang and in the heart of black holes. In these extreme environments, a massive amount of matter is crushed into a microscopic point. Here, the scales of quantum mechanics and gravity intersect. When physicists try to combine the math of both theories at a singularity, they get infinity's mathematical nonsense that suggests our theory is incomplete. Scientists have long sought a theory of quantum gravity to reconcile these two conflicting views. This would be a theory of everything that can describe the birth of the universe without breaking down. One exciting idea that emerged from this search is the no-boundary proposal championed by the late physicist Stephen Hawking and his colleague James Hartle. They attempted to apply quantum mechanics to the entire universe at once. According to this theory, the universe did not emerge from a sharp singularity. Instead, space and time are finite but limitless. To understand this, consider the surface of the Earth. The Earth has a finite surface area. You can measure it in square miles. However, it has no edge. Just as you can travel the Earth indefinitely without falling off the edge, you can travel the universe without colliding with a boundary. In the Hartle-Hawking model, as you go back in time toward the Big Bang, time does not come to a sharp stop at a singularity. Instead, due to quantum effects, time loses its distinctiveness and behaves like another dimension of space. The beginning of the universe would be a smooth point similar to Earth's North Pole. The North Pole is a point, but there is nothing singular or broken about it. It is just the point where the lines of longitude meet. In this model, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. There is nothing north of the North Pole, not because it is an edge, but because the geometry of the Earth makes the question invalid. Similarly, time essentially rounds off at the beginning. This proposal elegantly removes the need for a singularity and the problem of a start in time. This is a pretty good way to get around the singularity problem at the beginning of the universe. Like the other theories we have discussed, the no-boundaries proposal is not without criticism and is still the subject of ongoing research. Nevertheless, it represents an intriguing attempt to bring together worlds incredibly large and incredibly small, pushing the boundaries of our understanding of the origin of the universe. Now let us look into the field of string theory, a theoretical framework that attempts to solve the conflict between gravity and quantum mechanics by rewriting the definition of matter itself. In this framework, the fundamental building blocks of the universe are not point-like particles as traditionally believed, but incredibly tiny, one-dimensional entities called strings. These strings are so small that they are effectively invisible to even our most powerful microscopes existing at the Planck scale. The beauty of this theory lies in its simplicity of design but complexity of execution. Each string can vibrate at different frequencies and resonances, just as the string of a violin produces a different musical note depending on how it vibrates. These cosmic strings produce different particles based on their vibrational patterns. When a string vibrates in one specific mode, we perceive it as an electron. When it vibrates in another mode, it manifests as a quark or a photon. In this view, the entire universe is essentially a grand cosmic symphony where all matter and forces are just strings singing on different notes. However, string theory does not stop there. The mathematics required for these strings to vibrate consistently predicts the existence of more than the three spatial dimensions with which we are familiar. While we experience length, width, and height, string theory requires 10 or even 11 dimensions to function mathematically. These additional dimensions may be compacted or curled up so tightly that they are hidden from our perception. Imagine looking at a garden hose from a great distance. It looks like a one-dimensional line, but if you walk closer, you see it has a circumference, a second dimension curled around the first. Similarly, the extra dimensions of string theory are thought to be curled up at every point in space, fundamentally affecting the fabric of reality and determining the physical constants of our universe. In the context of our topic regarding the origin of the universe, one variant of string theory known as the pre-Big Bang scenario, or the ekpyrotic model, offers a radical alternative. This model suggests that our universe may have been created by the catastrophic collision of two three-dimensional worlds floating in a higher dimensional space. These worlds are referred to as branes, short for membranes. Imagine two sheets hanging parallel to each other on a clothesline. If the wind blows, they might touch. In the ekpyrotic model, our universe is one such brane. The theory suggests that the Big Bang was not a beginning from nothing, but the energetic result of two branes smashing together. What happens after such a collision? The kinetic energy of the impact is converted into the matter and radiation that fills our universe. The two branes bounce off and drift apart, cooling down as they separate, only to be drawn back together by mutual gravitational attraction to collide again billions or trillions of years later. This suggests a cyclic universe where the Big Bang is actually a big clash that happens repeatedly, perhaps creating another universe with each impact. So what was there before the Big Bang? Well, in this model, it could have been another universe similar to ours, existing on a brane parallel to ours, in a higher dimension preparing for impact. And yet string theory itself, although incredibly elegant and capable of combining quantum mechanics and gravity, has no empirical evidence. It remains a mathematical masterpiece without experimental confirmation. Since we cannot access higher dimensions or see strings directly, such things are very difficult to verify, leaving us in the realm of high-level theoretical speculation. But what if we choose a different approach? Instead of looking for a universe that preceded ours, what if we reconsider the very notion of nothingness? When we think of a vacuum or empty space, we often imagine absolute nothingness, a void devoid of all substance. But in the world of quantum mechanics, the vacuum is far from empty. Due to the Heisenberg uncertainty principle, energy values can fluctuate momentarily. This creates a bubbling soup of particles and antiparticles that spontaneously arise from the void and then almost immediately collide and destroy each other, returning their energy to the vacuum. This phenomenon is called vacuum fluctuations, or virtual particles. It means that on the smallest scales, space is not smooth and empty, but a turbulent froth of activity. The vacuum fluctuation model, also known as the quantum fluctuation model, suggests that our universe may have originated from one of these rare high-energy fluctuations. Just as a bubble can form in boiling water, a tiny bubble of false vacuum could have inflated into the universe due to the principles of quantum mechanics. In physics, a false vacuum is a region of space that appears stable but holds a tremendous amount of potential energy, unlike a true vacuum, which is at the lowest energy state. Such a bubble, due to a phase transition or quantum tunneling, would begin to expand rapidly. This expansion is driven by the energy stored within the vacuum itself. As the bubble expands, its edges would be pushed outward by negative pressure, causing the space within to stretch exponentially in a process we call inflation. Inside this bubble, the pent-up false vacuum energy would eventually decay and be transformed into matter and radiation, giving rise to stars, galaxies, and eventually you and I. So what was there before the Big Bang in the vacuum fluctuation model? It could have been a primordial quantum vacuum, a timeless sea of short-lived particles and antiparticles, appearing and vanishing in the dark. Our universe was just one random bubble that managed to survive and grow into something bigger, while countless others might have collapsed back into the foam. Now, while the vacuum fluctuation model is an exciting possibility, it also raises difficult questions that challenge its validity. For example, why did this particular bubble expand while others did not? Probabilistically, the creation of a universe as large and ordered as ours from a random fluctuation is incredibly unlikely compared to the creation of a smaller, simpler universe. This is known as the Boltzmann brane problem. Furthermore, how do we reconcile the idea of an eternal quantum vacuum with the apparent age of our universe and the arrow of time? But as we delve deeper into the world of quantum physics, we find that it holds more intriguing possibilities for cosmic origins. One of these possibilities is related to the field of research that attempts to fix the mathematical breakdown of the Big Bang singularity. This brings us to the next model, the Big Bounce theory. Imagine a universe that expands, contracts, then bounces back elastically like a ball hitting the floor. That is the basic idea of the Big Bounce theory. Unlike the standard Big Bang model, which traces everything back to a singularity, a point of zero size and infinite density, where all the laws of physics cease to exist, the Big Bounce theory argues that the universe never reaches that breaking point. Instead, it suggests that our universe may have been born from the remnants of an earlier contracting universe. In this model, the universe is not compressed into a singularity. This avoidance of the singularity is largely based on a theory called loop quantum gravity. This theory proposes that space-time is not smooth and continuous like a sheet, but is made of discrete atoms of space. Because space is granular, there is a limit to how small it can get. You cannot crush these atoms of space into nothing. When the universe contracts to this critical density, quantum repulsive forces take over. Gravity, which is usually attractive, becomes repulsive at these extreme densities. Instead of crushing into oblivion, the universe rebounds. It returns to a very small but finite size and begins to expand again, leading to what we now call the Big Bang. This event was not a beginning, but a transition. This theory, like the oscillating universe theory, postulates a universe with no beginning and no end, but with an infinite cycle of expansion, contraction, and rebirth. In this way, it circumvents the singularities that plague the other models, making the math consistent without breaking the laws of physics. However, unlike the classical oscillating universe theory, which relies on standard gravity and leads to entropy problems, the Big Bounce focuses specifically on the transition point, the quantum gravitational bounce between contraction and quantum expansion. So how does quantum mechanics fit into this? Quantum effects are thought to play a significant role on the very small scales at which rebound can occur. According to quantum mechanics, particles can tunnel through barriers even if they have no classical energy to do so. Some theories suggest that the universe could use a similar quantum tunneling effect to bypass the singularity entirely, moving from a contracting state to an expanding one, without ever passing through a state of infinite density. Again, this theory is highly speculative and faces significant problems, both theoretical and observational. The primary challenge is detection. Can we find evidence for a previous phase of contraction in our present universe? Some scientists look for specific patterns in the cosmic microwave background radiation that might be scars or imprints left over from the previous universe. Additionally, can we develop a fully functioning quantum theory of gravity that can handle these extreme conditions mathematically? However, the Big Bounce theory is not without its flaws. The physics of what can make the shrinking universe come back to normal is still being rigorously investigated. Understanding how this process can occur without violating the known laws of physics, specifically the laws of thermodynamics, which dictate that disorder must increase, is the main obstacle to this theory. If disorder increases with every bounce, the cycles cannot last forever. The Big Bounce theory does not yet fit perfectly within our traditional notions of time and causality, but it offers a path that avoids the breakdown of physics at the start of time. However, as always in science, there are competing theories that are even more exotic. For example, our universe could have been born from a cosmic object that we have already discovered but barely understand. Something mysterious, all-consuming, but perhaps also creative. I am speaking of a black hole. Black holes are the mysterious giants of the universe, formed by the collapse of massive stars. They are regions of space where gravity is so strong that nothing, not even light, can leave it once it crosses the boundary known as the event horizon. The base of a black hole, according to the general theory of relativity, is a singularity, a point where density becomes infinite and the curvature of space-time reaches an extreme degree. In standard physics, this is a dead end. Matter falls in and is crushed out of existence. But what if these cosmic entities are not the end, but rather the beginning? This hypothesis, often associated with physicist Lee Smolin, suggests that singularities inside black holes could give rise to new, expanding universes. When a star collapses into a black hole, the core creates a region of extreme density, similar to the conditions of the Big Bang. Some physicists speculate that instead of leading to a dead end, the matter falling into a black hole might bounce back out into a new dimension, creating a baby universe that expands on the other side of the singularity. Thus, our universe could be the inner part of a black hole belonging to another parent universe. In this model, the Big Bang would correspond to the formation of a black hole singularity in the parent universe. From the perspective of an observer in the parent universe, the star collapses and disappears. But from the perspective of the baby universe inside the event horizon, a Big Bang occurs and space starts expanding. The expansion of our universe corresponds to the internal growth of the black hole, or the creation of a white hole, which is the theoretical reverse of a black hole spewing matter out rather than sucking it in. This theory introduces the fascinating concept of cosmological natural selection. If universes are born inside black holes, then universes with physical laws that allow for the formation of more black holes will have more offspring. This might explain why our universe seems so perfectly tuned for the black holes to formation of stars, since stars are the precursors to black holes. So what was there before the Big Bang? It could be the inside of a black hole in another universe. We might be living inside the event horizon of a supermassive object existing in a higher reality. And maybe every black hole in our universe, from the supermassive ones at the centers of galaxies to the smaller stellar mass ones, can give birth to a new universe inside itself, creating a cascading family tree of realities. Of course, this idea, like all those we have discussed, is a hypothesis and not without problems. The biggest hurdle is information. Because nothing can escape a black hole we can never communicate with or observe the parent universe, and no one inside a baby universe we create could ever communicate with us. How can we test this theory if the evidence is forever locked away? Can we observe the effects of the parent universe, perhaps as a directional pull in our own expansion? And how do we reconcile this with our current understanding of black holes and singularities? Loop quantum gravity, or LQG, is a theoretical framework aimed at reconciling the two giants of 20th century physics. On one side, we have quantum mechanics, which describes the very small chaotic world of atoms and subatomic particles. On the other side, we have general relativity, which describes the very large, smooth curves of stars, galaxies, and gravity itself. These two theories act like oil and water, refusing to mix mathematically. Loop quantum gravity attempts to bridge this gap by proposing a radical idea that space itself is not continuous. In our daily lives, space looks smooth. If you move your hand from point A to point B, you pass through every infinite point in between. However, LQG implies that this smoothness is an illusion created by our size. It suggests that space consists of tiny, indivisible loops or grains. Just as a piece of fabric consists of interwoven threads that look like a smooth sheet from a distance, space is woven from these quantum loops at the Planck scale. When applied to the origin of the universe, loop quantum gravity evolves into a specialized field known as loop quantum cosmology. This framework offers a rebound scenario similar to the Big Bounce which we discussed earlier, but with a firmer mathematical foundation. In fact, loop quantum cosmology provides a specific quantum mechanical description of the evolution of the universe, including the mechanics of the bounce itself. Instead of collapsing into a singularity, a point of zero volume and infinite density as required by the traditional Big Bang theory and general relativity, the universe behaves differently when it gets incredibly small. As matter is crushed together, the grains of space cannot be compressed any further. At this critical density, quantum gravitational effects become significant. Gravity, which is usually an attractive force, flips and becomes a repulsive force, counteracting the contraction. Then the universe bounces back elastically and begins to expand again. This means that our universe may have undergone a series of expansions and contractions, each of which began with a quantum jump rather than a singularity. So what was there before the Big Bang? From the point of view of loop quantum cosmology, it may be another phase of the universe, specifically the contraction phase, which preceded the quantum jump. This leads to the fascinating concept of a quantum bridge. This bridge represents a transitional phase connecting our universe with its predecessor. Instead of hitting a wall at the singularity where math breaks down, the universe undergoes a quantum leap. This transformation from contraction to expansion can be seen as a tunnel or a bridge from the old universe to the new one. This quantum bridge is not a physical bridge in the conventional sense made of steel or stone, but a phase of the evolution of the universe controlled by the equations of quantum gravity. It allows information and energy to pass through the bottleneck without being destroyed. So what is beyond the Big Bang? According to loop quantum cosmology, the previous universe is connected to ours by this quantum bridge. Although this theory effectively eliminates the singularity at the Big Bang and offers an elegant quantum description of the evolution of the universe, it still faces considerable difficulties. The mathematics are incredibly complex, and simpler models often have to be used to make calculations possible. Nevertheless, if it is correct, it offers us an amazing picture. We see a universe with no beginning and no end, experiencing infinite cycles of contraction, jumping, and expansion forever, reinventing itself. Although these theories, from the multiverse to loop quantum gravity, offer intriguing possibilities for the most part, they are still in the realm of speculation. Each has its mathematical strengths and its observational weaknesses, and none of them yet has conclusive experimental evidence in its favor. Even as we approach the answer to what was before the Big Bang, we should expect that each answer will open up even more questions. This is the nature of scientific inquiry. But the beauty of science lies in the process of exploration and discovery itself, not just the final destination. Researchers around the world tirelessly study these theories and improve their models utilizing particle accelerators and space telescopes to test the edges of these ideas. The study of even one theory goes a long way towards advancing the whole picture of our reality. So what happened before the Big Bang? In a nutshell, at this point we do not know for sure. It remains one of the greatest unsolved mysteries. But whatever the answer, the search itself enriches our understanding and inspires us to keep looking. While we ponder the infinite beginnings of time, we must also look at the present activity in our local neighborhood. In the vast expanse of space among countless stars and galaxies, there is a whisper. It is the whisper of a distant star that has traveled light years to reach us here on Earth. This is not a science fiction tale, but a reality of our universe, and a testament to the continual growth of our understanding of the cosmos. Scientists eavesdropping on space have detected a specific signal. It is a coherent radio wave emanating from a star system not so different from our own. The star known as YZ Ceti is located just 12 light years away. In galactic terms, this is right next door. But it is not just any random noise. This signal carries a potential signature of a magnetic field very similar to the one that protects our own planet. This is the magnetic field that may envelop a rocky Earth-sized exoplanet known as YZ Ceti b orbiting the star. What could this mean? Could this distant world be more like our own than we have ever imagined? And what could it tell us about the search for life beyond our solar system? To understand this, we must go light years across the void to delve into the mysteries of radio signals in space and explore the critical role of magnetic fields on distant worlds. In the boundless silence of space, radio signals can, without guile, be called whispers. But what are these signals, and how do they propagate over such vast distances? Radio signals are a type of electromagnetic radiation. They are fundamentally the same as visible light, X-rays, or microwaves, but they exist at a much lower frequency and longer wavelength. They are generated by a variety of sources, from the explosive deaths of stars and the centers of active galaxies to artificial satellites and spacecraft. These signals travel at the speed of light, carrying information across vast distances in space. Unlike visible light, which is easily blocked by dust clouds, radio waves can pass through obstacles, allowing us to see into the hidden hearts of galaxies. They can tell us about the composition of stars, the presence of planets, and even the origin of the universe itself. But how do we detect these invisible signals? The answer lies in the technology of radio astronomy. We cannot use traditional glass lenses. Instead, we use radio telescopes. These are often massive dish-shaped antennas. Famous examples include the Very Large Array in New Mexico or the now-defunct Arecibo Observatory in Puerto Rico. These instruments are designed to detect and analyze radio signals from space. They are our ears to the cosmos, listening to the faint whispers of the universe. Specifically, the Very Large Array functions as an interferometer. It uses 27 separate antennas combined electronically to simulate a single massive telescope acting like a giant eye miles across. Once a signal is detected by a radio observatory, it is analyzed using sophisticated algorithms and computer models. These analyses can provide extensive information about the source of the signal from its location and distance to its physical properties like temperature and density. But radio signals from space are not just a scientific curiosity. They also have practical applications that ground us in reality. For example, radio signals from satellites are used for GPS navigation, weather forecasting, and Earth observation. They are an integral part of our modern technological infrastructure. So the next time you look up at the night sky, remember there is a whole symphony of signals playing out there. It is a cosmic conversation, an orchestra of data that we are just beginning to understand. Let us return to the constellation of Cetus, the sea monster, in which lies a star that whispers to us across light years. Her name is YZ Ceti. This star is a red dwarf. Red dwarfs are the most common type of star in the galaxy, but they are much smaller and cooler than our Sunday YZ. Ceti is located 12 light-years away, making it a close neighbor on a cosmic scale. But what makes YZ Ceti truly fascinating is not the star itself, but what revolves around it. At least 3 exoplanets are known to orbit around this small star, the innermost of which is named YZ Ceti b. This planet is of particular interest to astronomers. YZ Ceti b is a rocky Earth-sized exoplanet. This means it has a solid surface and a mass comparable to our home world. However, it orbits very close to its parent star. In fact, it is so close that its year, the time it takes to make one revolution around YZ Ceti, is only 1.6 Earth days. Recently, using the Very Large Array, scientists at Bucknell University, led by Professor Jackie Villadsen and her colleague J. Sebastian Pineda, detected a repeating radio signal coming from the YZ Ceti system. This was a groundbreaking observation. the signal was recorded at a frequency of 2 to 4 gigahertz. Crucially, it appears to be modulated by the rotation of the star and the orbit of YZ Ceti b. This synchronization indicates a direct physical interaction between the star and the planet. Specifically, it suggests an interaction between the stellar wind, the stream of charged particles flowing from the star, and the magnetic field of the planet. When the planet plows through the magnetic material of the star, it acts like a dynamo, creating powerful electrical currents that generate radio waves. This discovery could have major implications for our understanding of exoplanets and their habitability. Why is a magnetic field so important? On Earth, our magnetic field acts as a planetary shield. It deflects the high-energy solar wind and cosmic rays that would otherwise strip away our atmosphere and bombard the surface with lethal radiation. Without a magnetic field, Earth might look like Mars, a barren, dry world with a thin atmosphere. Therefore, finding a magnetic field on an exoplanet is a key step in finding a habitable world. Although YZ Ceti b is unlikely to be teeming with life due to its dangerously close proximity to its star, the detection of its magnetic field is a proof of concept. It demonstrates that rocky exoplanets can indeed maintain strong magnetic fields despite the intense tidal forces of their host stars. This detection is important because it provides a reliable method for discovering more life-friendly worlds in the future. But what does this specific signal really mean? And why are magnetic fields so critically important in our search for life elsewhere in the cosmos? To answer these questions, we need to look deeper into the invisible force fields that shape our universe. We often think of space as a vacuum, but it is threaded with these silent, invisible powers. Magnetic fields are a fundamental force of nature. On Earth, they are the silent guides that direct the hand of the compass, allowing for navigation long before satellites existed. They help migratory birds navigate their transcontinental journeys, sensing the field lines of the planet to find their way home. Most importantly, they protect our planet from the harsh solar wind, the stream of charged particles constantly erupting from the sunday. Without this shield, our atmosphere would be slowly eroded away. But magnetic fields are not just an earthly phenomenon. They play a crucial architectural role in the universe beyond the Earth. Our Sun, for example, has a complex and dynamic magnetic field that behaves very differently from the stable field of Earth. It is a twisting, churning mess of field lines that controls the activity of the sunday. It drives everything from the formation of sunspots, cooler, darker areas on the solar surface, to the violent eruption of solar flares and coronal mass ejections, which can fling billions of tons of plasma into space. On even larger scales, magnetic fields shape the structure of entire galaxies, acting as the skeleton upon which interstellar gas flows, directing the movement of material and influencing the formation of new stars in nebulae. But perhaps the most intriguing role of magnetic fields in space is their potential impact on planetary habitability. A strong magnetic field acts as a deflector shield. It can protect a planet from harmful ionizing radiation from its star, helping to maintain a stable, thick atmosphere, and perhaps even maintaining the pressure and temperature conditions suitable for liquid water and life. That is why it is so interesting to detect a potential magnetic field on the exoplanet YZ Ceti b. This is not just a technical achievement. It could provide valuable information about the atmosphere of the planet and its potential to support life. If a planet has a magnetic field, it likely has a liquid moving core, which implies internal heat and geological activity. But how exactly do magnetic fields affect the detection and interpretation of signals from space? How do we see a magnetic field light years away? To understand this, we need to delve a little deeper into the nature of radio signals and their interaction with magnetism. Radio signals are a type of electromagnetic wave. This means they are composed of two components, an oscillating electric field and an oscillating magnetic field, moving together through space. These fields are not passive. They can interact with other magnetic fields they encounter on their journey. When a radio signal passes through a region of space containing a magnetic field and charged particles, it can be altered in various ways. Its direction can be slightly changed, a phenomenon known as deflection, similar to how a lens bends light. More importantly, its polarization can be changed. Polarization refers to the orientation of the electric field of the wave. Imagine a wave moving like a ribbon twisting in the wind. When a polarized radio wave passes through a magnetized plasma, its plane of polarization rotates. This is a specific physical effect known as Faraday rotation. The stronger the magnetic field, the more the wave rotates. Additionally, its frequency, the number of waves passing through a point in a given time, can be shifted due to interactions with moving plasma. These changes leave a fingerprint on the signal. By studying these subtle alterations, scientists can reverse engineer the data to infer properties of the magnetic field, such as its strength, its orientation, and the density of the plasma it passed through. This allows astronomers to map invisible magnetic structures across the galaxy. But magnetic fields can also pose problems for detecting signals from space. The universe is a noisy place. Magnetic fields can cause interference, generating background static that makes it difficult to detect a faint, artificial or natural signal. They can distort the signal, making it difficult to interpret the original message or data. This is why the study of magnetic fields is so important in the field of radio astronomy. By understanding how magnetic fields affect radio signals, scientists can develop methods to correct these effects and extract valuable information hidden in signals from space, effectively cleaning up the noise to hear the whisper underneath. To better understand the influence of magnetic fields in creating favorable conditions for life, let us turn our gaze closer to home, to a familiar red-headed neighbor in our cosmic backyard. Mars, the red planet, has long captured our imagination with its towering volcanoes like Olympus Mons and its deep canyons like Valles Marineris. The surface shows clear geological evidence of ancient riverbeds and lakes, hinting that liquid water once flowed there. It is one of the most intriguing places in our solar system because it looks like a failed Earth. Mars presents us with a mystery. Unlike Earth, which has a strong global magnetic field generated by a churning liquid iron core, Mars possesses only a very weak and inhomogeneous magnetic field. It is patchy and scattered. This has serious implications for the atmosphere of the planet and its ability to support life. The magnetic field of Mars is not created by an active dynamo in its core like the Earth. The Martian core likely cooled and solidified billions of years ago, shutting down the generator. Instead, the magnetism we detect today is the remnant of magnetism trapped in the crust of the planet. It is fossilized magnetism preserved in the rocks from a time billions of years ago when Mars actually had a global magnetic field. Without a strong, active magnetic field protecting it, the atmosphere of Mars is directly exposed to the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, emitted by the Sun at speeds of nearly 1 million miles per hour. When these particles hit an unprotected atmosphere, they impart energy to the gas atoms, knocking them loose and dragging them into space. Moreover, new models presented by R. Sakata of the University of Tokyo and other researchers suggest a counterintuitive finding. We might assume that a weak magnetic field is better than nothing, but the physics suggests otherwise. A weak magnetic field, like the one Mars possesses after its dynamo turned off, could actually lead to a more rapid loss of atmosphere than if there were no magnetic field at all. Modeling has shown that a weak magnetic field results in the fastest rate of atmospheric ion loss, up to 6 times faster than a planet with absolutely no magnetism. The reason lies in how the magnetic field lines connect. The weak magnetic field lines of the planet can reconnect with the magnetic field lines carried by the solar wind. Instead of forming a bubble that deflects the wind, this reconnection creates open pathways, essentially magnetic highways, that allow the solar wind to reach deep into the atmosphere. The solar wind then energizes the atmospheric ions, and these magnetic highways guide them straight out into deep space over the night side of Mars. This suggests that the remnant magnetic field of Mars may have actually hastened the planet's transformation into the cold and barren world it is today, acting as a catalyst for its own destruction. Over billions of years, this process caused Mars to lose much of its thick atmosphere, a process known as atmospheric stripping. This turned Mars from a potentially warm and wet world in its early history, where life might have started, into the cold, dry, and irradiated planet we see today. The case of Mars provides a vivid illustration of the importance of magnetic fields to a planet's habitability. It is a cautionary tale. It shows us that without a strong global magnetic field, a planet, even one as Earth-like as Mars in terms of size and composition, can lose the very things that make it habitable: its atmosphere and its water. By the way, we have already looked at the problems and potential solutions for terraforming Mars and making it a second home for humanity in a separate video on this channel. But if we want to find a planet that does not need terraforming, we must look further afield. Exoplanets, planets orbiting stars outside our solar system, have recently become a major focus of astronomical research. With more than 5,000 confirmed exoplanets discovered to date, they offer a wealth of opportunities to learn about the diversity of the planetary systems in our galaxy. One of the most exciting developments in this field was the discovery of the first known magnetic field on an exoplanet. This occurred in late December of the year 2021 by an international team of astronomers who used the Hubble Space Telescope for their research. The magnetic field was discovered on a Neptune-sized planet called HATP-11b. HATP-11b is located about 123 light-years away in the constellation of Cygnus the Swan. It is classified as a hot Neptune. This means it is a type of exoplanet that is similar in size and composition to Neptune, but it orbits much closer to its star, resulting in scorching temperatures on the planet's surface. Because it is so close to its star, the atmosphere is expanding and escaping into space. The astronomers used Hubble to observe the planet as it passed in front of its star. They detected carbon ions surrounding the planet in a massive cloud. Crucially, they observed that these ions were being swept away in a long tail that extended far away from the planet. The shape and density of this tail could only be explained if the planet had a strong magnetic field pushing against the solar wind of its host star. The detection of a magnetic field on HATP-11b was a groundbreaking discovery. It showed that exoplanets can generate magnetic fields just like planets in our solar system, and that we have the technology to detect them. As we mentioned earlier, studying the magnetic fields of exoplanets can provide valuable information about their internal structure. A magnetic field suggests a liquid interior which affects models of planetary evolution. Furthermore, it gives us data on atmospheric properties and potential habitability. For example, a strong magnetic field can protect a planet's atmosphere from stellar winds, helping to preserve conditions that could support life even in harsh radiation environments. That brings us back to YZ Ceti b, the Earth-sized exoplanet, from which a radio signal was recently detected. If this signal is indeed indicative of a magnetic field interaction, it can have a major implication for our understanding of this exoplanet and its potential for life. It would be the first strong evidence of a magnetic field on a rocky Earth-sized world outside our solar system, proving that Earth is not unique in possessing this protective shield. Traveling through space from the familiar landscapes of Mars to the far reaches of YZCT, we have truly come to realize the invisible power of magnetic fields. We see their profound effect on the evolution of planets and their potential to harbor life on them. The field of studying signals from other galaxies has grown rapidly over the past few years, extending our hearing range beyond the Milky Way. For example, the Giant Microwave Radio Telescope, or GMRT in India, recently detected a faint signal from the most distant galaxy to date. This signal originated from neutral hydrogen gas, when the universe was only a fraction of its current age. Just as the signal detected by YZCT opened a window into exoplanetary magnetic fields, this distant signal opens a window into the early universe. These discoveries remind us how much we still have to learn about our world and the cosmos at large. As we look to the future, the study of signals from other galaxies and star systems will continue to be the focus of space research. Each signal carries the potential for new discoveries, whether it is the signature of a magnetic shield protecting an alien world, or the whisper of hydrogen from the dawn of time. So when we look up at the night sky, let us remember that we are not just looking at stars and galaxies. We are looking at a universe filled with unseen forces, whispered signals, and hidden possibilities. And as we continue to listen and explore, who knows what we might discover next.